The next type of graph we'll look at is known as an order requirement graph. And this is going to be a directed graph, so a graph with directions. And this is we're going to use this to describe the tasks that make up a job. And we're going to use the directions for tasks which must be completed before the other tasks can be started. So for example, these boards had to be put up before these boards were put up. These boards took a lot longer to put up than they should have because of all the leveling and inconsistencies in the walls, but that's okay. So right here we have a bunch of tasks, and some have to be done before others. So an example of what this may look like is this. Very frequently in these we will describe, well, I'll mention that in a moment. Let's look at the graph first. So this job has 8 tasks. I need that circle to be bigger. There's a reason I'm using big circles for this. Maybe I can put that up there. No, I don't like how that looks. Too hard to grab. So here is task 1. So here we have 6 of our tasks. So right here what this means is task 1 must be completed before task 2 can be started. And task 2 must be completed before task 5 can be started. Task 2 must also be completed before task 3 can be started, and so on. But let's put another couple tasks in here. Let's say we have a task 7 and a task 8. Task 7 and task 8 can be started regardless of what else is already done. Just like task 1, we can start task 1 at the beginning. Task 7 and task 8 do not. Nothing else relies on task 7 and task 8. We can start them at the beginning. Now, generally in these jobs, these tasks can be described by how long they take. So let's describe that using minutes or numbers. Maybe these are seconds, or maybe these are years. They're units of some time. Task 1 takes 8 units of time. Let's use minutes. Task 2 takes 6 minutes. Task 5 takes 5 minutes. Task 3, 9. Task 4, 4. Task 6, 3 minutes. Task 7 takes 5 minutes, and task 8 takes 7 minutes. Well, that's great. What can we do with this? So a critical path in an order requirement graph is a longest path. So in the other examples we've been doing, we've been trying to minimize time. Here we're not trying to maximize time. What we're going to do is try to figure out how long this job must take, given the information we have. And the critical path will tell us that. It is a longest path. In this case, the length of the path will be given by the time it takes to complete all the tasks on that path. So a critical path in an order directive graph, order requirement graph, is a longest path. So right here, let's look at this example. Let's look at all of the paths that must be done in this. Well, first, let's start at task 1, and then you go to task 2. Well, here you can go up to 5 and 6. So there's one path. So let's make a chart, I guess. I'm not going to have room for that. Well, let's make a chart. I don't need the word chart for chart. Path. So path through the order requirement graph, and let's call this other one time. So the amount of time it takes to go through that path. So the one path we just described, task 1, task 2, task 5, task 6. So T1, T2, T5, T6. And how long does that take? 8 plus 6 is 14, plus 5 is 19, plus 3 is 22. And then I make sure I said those numbers right. 8, 6, 5, 3, 14, and 8. Yes, 22. Okay, let's look at another path. Task 1, 2, 3, 4. 8. Well, I'll write that down first. Task 1, task 2, task 3, task 4. Takes 8, plus 6 is 14, plus 9 is 23, plus 4 is 27. So that's 27 minutes to go through that task. So that covers that part of the graph. But we also have these other tasks, these other paths through the graph down here to consider. Task 7 is its own path. That takes 5 minutes. Task 8 is also its own path. That takes 7 minutes. And this thing we define as a critical path is the longest path through the graph. So in this case, so here, T1, T2, T3, T4 is the critical path. In this case, it's the critical path. In general, for a graph, it's a critical path because you might happen to have two things that are both 27. Like, for example, if T7 took 27 minutes, then there would be two critical paths. And the job would take at least 27 minutes. So that is a critical path, and the time it takes is 27 minutes. Now, why do we want these critical paths? Well, when we're completing a job, it would be nice to know if everything went perfectly and we had as many people as possible, how long would the job take at minimum? Well, in this graph, what was it? It was something like this. Something like this. Well, in this graph, this entire task, to complete that first task, took only 22 minutes. But there was another path you could take through that took longer. So that other path that took 27 minutes means that, sure, we can complete this task up here in 22 minutes, but we can't finish the entire job in 22 minutes because this line of work takes 27 minutes. And similarly, we can't finish in 5, or we can finish these tasks in 22 minutes. But overall, the job would take at least 27 minutes. And task 8 would take 7. Task 7 takes 5. So let's look at another couple examples of finding these critical paths. There are methods in general for general graphs, for general order requirement graphs. There are methods of finding the critical path. We won't actually go through any of the methods. We will just largely list them. So let's look at this example. After landing, an airplane must go through the following tasks with the given graph. So example, after landing, an airplane must go through these tasks. A, B, C, D, E. A is unload passengers. Do I need to write that down? You can write these down if you want. I'm not going to write these down because what these tasks actually are doesn't matter. A is unload passengers. B is unload cargo. C is clean cabin. D is load new cargo. E is load new passengers. Task A takes 13 minutes. Task B takes 25 minutes. C takes 15 minutes. D takes 22 minutes. E takes 27 minutes, and the order requirement graph looks like this. And I'll put the times in these. 13, 15, 27, 22, 25. So here we'd like to find the critical path. Now, when I saw this in the textbook, my first thought was B is unload cargo, E is load new passengers. And I thought, well, why would you need to unload cargo before putting new passengers on the plane? And the cargo's like under the plane, I think. I don't do airplanes much. I am very against airplane. But this says that you must unload cargo before loading new passengers. And the textbook actually addressed that, and they said it was because of, well, they said because of regulation or union requirements. So in case you're wondering why B is done before E, either regulation or union or both. But we want to find the critical path. So let's look at all paths. Let's say path and time. Well, there's a path, ACE. ACE takes 13 plus 15 plus 27. 13 plus 27 is 40. 40 and 15 is 55. Well, here's a path, B to E. B to E takes 25 plus 27. 52. Here's a path, B to D. B to D, 25 plus 22, 47. So here the critical path is A to C to E, meaning unload passengers, clean cabin, load new passengers is the critical path for this airline when this book was written. So here, A, C, E is the, in this case, critical. I spell critical. Path. So now these first two examples, relatively small graphs, relatively easy to list these compared to large graphs. So I'm not going to write directions and information on this. We'll just say find the critical path for the graph I'm about to draw. It has a nine tasks. Find the critical path. Let's see, board organization. Let's do it like this. Is that everything? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. So here we have all these tasks. Let's call them A through I. with associated times. We have 6, 5, 2, 9, 3, 8, 7, 6, 7. And here, find a critical path. So here we have to be quite careful in our paths. We need to make sure we don't miss any. It might actually be a good idea to pause this and try yourself and see, at least see if you get all the paths. I don't know how many there are off the top of my head. But first, A to B to C. Okay? A to B to C. All you can do from B is go to C. So next we have A, E. But what can we do after E? A, E, C. A, E, F. A, E, I. Okay? That's all you can do from A, because you can't go down to H or to G or D. D. You can go to E. D, E, you can go up to C, or you can go over to F, or you can go down to I. How about from G? G, you can go up to E, up to C. I'm gonna, I guess I'll continue on this one. G, E, C. Or you could do G, E, F. Or you could do G, E, I. Or you could do G, H. And from H you can only go from G to H to F, or G to H to I. So I'm going to continue that over here. And we listed all these, now we have to add lots of numbers there. A, B, C is 13. A, E, C is less, what is that, 11? A, E, F is 17. A, E, I is 16. D, E, C is 14. D, E, F is 20. 17 plus 3 is 20. D, E, I is 19. G, E, C is 12. G, E, F is 18. G, E, I is 17. It was nice that G and E added to 10. That made that easier. G, H, F is 21. G, H, I is 20. And remember here, the critical path is not the smallest. My middle name does not start with E, it starts with K, so I'm not too unhappy that that's not chosen. For the record, in case you didn't, my first name starts with A, and my last name starts with C. But my middle one is with a K. But we do not want the smallest one here, because remember, these are tasks to complete a job, and we want to know how long the job definitely has to take. Well, going through G to H to F must take 21 minutes. So G, H, F is the critical, in this case, the critical path. And the time it takes is 21. So these can be made quite complicated. So try the examples in the worksheet and see how they go, because these are, I think the thinking you go through for these is useful thinking. So see how they go.